Okay, all right. Well, welcome everybody. It's just a minute after 7 o'clock on Tuesday night, September 27th, and I just want to welcome you to the third annual UC Santa Barbara Natural Reserve System Fall Seminar Series. My name is Marianne Whitman. I'm the Executive Director of the UC Santa Barbara Natural Reserve System, and we are so pleased to be with you again tonight. I just want to say thank you to everybody out there in the audience. As I mentioned, this is our third iteration of this, and it just keeps growing in popularity every year. And I think that's because of you. So thank you for spreading the word. And again, thank you for attending tonight. I want to just start out by giving a shout to all the UCSB undergraduate students out there. So the quarter just started. Everybody's coming back to campus right now, and I'm sure it's an overwhelming time. You're getting all your syllabus and your homework assignments and your room assignments and all those things. And that's all real exciting. And I'm just so glad that you're taking the time to join us tonight with all that you have going on. And I hope that you can lean back and relax and really just take in Cole Point Reserve and our most exciting speaker that we have for you tonight, Professor Dar Roberts of the UC Santa Barbara Geography Department. So you're in for a treat. Before we get started, I just wanted to showcase and highlight a little bit what we've got for this term. So our first talk is tonight. They're every Tuesday night from now until November 15th from 7 to 8 p.m. So please sign up and join us. And we've got a lot on the plate. We're going to talk about otters, art, space, plants, bumblebees, bumblebee guts, sage grouse, and more bees. So we've got a lot of bees, lots of things out there. And you'll also hear from all of our reserve directors who will tell you about what's going on in our reserves this year too. So please, again, do join us. Before I introduce our reserve director, who will introduce our speaker tonight, I just wanted to do a little bit of housekeeping and give you all a little bit of instructions for the evening. So we're going to have really kind of two presentations, one from our reserve director at the Cole Oil Point Reserve, and then two from our featured speaker. We'll have about maybe 10 to 15 minutes at the end for all of you to participate with us. So look at the bottom of your Zoom screen. There's a Q&A function there, and that's where you should drop your questions. The Q&A session will be moderated, and you could ask questions either of our reserve director, Chris, or our speaker, Dar, for anything that comes to mind about what they presented to you tonight, or if you want to get involved with the reserves. So without further ado, I did want to just give a little introduction to our reserve director, Dr. Cristina Sandoval, who is going to tell us a little bit about Cole Oil Point Reserve. But I kind of want to say my favorite thing about Cole Oil Point Reserve before I kick it over to Chris. And I think one of the neatest things about Cole Oil Point Reserve is that it's so close to main campus, and so that all of our UCSB students can really just, get on their bike or get on their feet and walk over there and really experience what it's like to see just such an amazing habitat. And Chris and her staff offer internships to UCSB undergraduate students, and they mentor about 60 students per year and also provide stipends for those students. So come on out to Cole Point Reserve, all you UCSB gauchos out there, and see what's going on at the reserve. And so with that, I'm going to turn it over to you, Chris, and why don't you take it away? Thank you.
Share screen here. Thank you guys, and welcome to the seminar series again, and I hope you're having a good evening so far. So my name is Cristina Sandoval. I have been managing Cole Point Reserve for 26 years. I came here pregnant, so I know exactly how long I have been here. So Cole Point is a small reserve compared to most of the reserves in the system, but yet we have so much use and so much interesting things going on. We have a wonderful staff, Jessica, Kip, and Tony, and lots of volunteers as well. And we also have a brand new addition to the reserve, Kayo, who is about 1 year old now. Yeah, not even 1 year, and just simply adorable. So, if for anything, come check him out here. So, a Coal Point Reserve is, as you can see here, very close to campus, close to IV and Elwood. So, because of that, we have such great opportunities to receive students and researchers in an informal way. They don't have to plan a long trip to come here and be able to use the reserve. But in the past, this is a photo from 1929. Most of the reserve was actually graded away, devegetated for ranching, but parts of the dune and the Devereux Slough remained. And so there was a lot of impacts back then, and a lot of our work is trying to revert those impacts. And then more recently, ranching was changed to development. So the reserve is still there, but now it's surrounded by development. So some of the work that we do also is related to how do you preserve this pristine area when there's all these changes going on around the reserve. But today, we have a reserve that is protected in perpetuity, and it's beautiful and restored. And there's a lot of interesting habitats and interesting species here that allow for people living in Goleta or working at UCSB to come visit and learn about them. So one of our jobs that we really enjoy doing is to share all these marvelous things about Coal Point Reserve with you, the visitors, and with our students. And like Marian said, students are the best part of what we have here. There's so many of them that go through our programs and they learn hands-on things about restoration, conservation, monitoring, research in general. And through that time, they teach us what the new generation thinks about everything and challenges, and we just absolutely love that. So we're constantly changing or adding new things to our list of things that we do. We have some regular programs like the conservation of snowy plovers that most of people already know, and restoration and monitoring of water quality. But every year we add something new. So we have three main things that we are focusing on this year. Is we're improving and diversifying our internship program. We've learned that many students end up giving up of biology simply because they don't have a field experiences. So we're trying to revert that and making that easily and accessible for everyone. We're trying to improve our knowledge of biodiversity. Believe it or not, we already know that we have about 1,000 species on Coal Point Reserve, and that's just the tip of the iceberg. And as we face changes like climate, for example, how do we know how to protect these things if we don't know if they're here? So we needed to speed up how we do that. And one way we're going to do this is using DNA sequencing to identify these species. We're also posting information on iNaturalist and eBirds so we can disseminate this information to you and make it accessible to everyone. In our dream life, every one of you would be an expert on the reserve's biodiversity. So you can help us get that information out there. And we're also trying to find solutions to changes in climate and urbanization. And we feel that these challenges that we have here are actually a really good opportunity for us to try to bring some light into issues that are happening into the entire world. This issue of how do you protect our environment and live and coexist is an issue that happens everywhere. But if you would like to learn more about the reserve, please go to our website. We have an active Instagram and Facebook page where we put cool things. You can take a guided tour the first Saturday of each month. You can volunteer and support the reserve, and you can volunteer in many different ways. Just tell us you want to volunteer and we'll find something fun to do. And get in touch with us. Share your ideas and what you think about the reserve, your passions, things you think we could do better. We would love to hear from you. And now it's my great pleasure to introduce Professor Dar Roberts. And Dar, I'm going to read it because your field is very difficult to say. So Dar is a faculty at Department of Geography at UCSB, where he investigates the Earth and its characteristics through a variety of tools, such as remote sensing, spectrometry, and spectroscopy. I got it. Professor Roberts also uses the NRS extensively, both for research and for teaching. And today he's going to talk about some of his work, and you see how his love for his work goes through his students and how he inspired so many students to become researchers themselves. With that, please, I will stop sharing my screen, and Dara, go ahead and start yours.
Helpful to unmute first, then share screen, then get this going. Here we go. So hopefully everybody can see this. Yeah, so I'm really pleased to have the opportunity to talk about some of the kinds of things we've been doing at Colwell Point. Today, I'm really going to be focusing on some of the environmental observations we've been making and how we've been using those to monitor change at Colwell Point. And I think it's very appropriate, the strong educational focus that we've seen from Chris as well as Marian, because that's a lot of what I'm going to do today. Is I'm going to talk about how I use this particular reserve, but I use other reserves as well in teaching. And so what I'm really going to focus on is a class I teach, and I'll be teaching it actually this coming up spring, called Measuring Our Environment. And Measuring Environment was actually inspired by a different class. I was teaching another class called Earth System Science, and this was an active learning class where there was a modest amount of lecturing, but what there really was is students used computer programs to design research questions and then did research, real research, and then presented it to the class. And I thought, well, this is really a great way to learn, but can't we do this with measurements and not just models? And so I thought, well, yeah, and what's a great kind of environment to do this? Well, it's the environment we live in. And so working with Chris Still and in my department, we crafted a proposal that was funded to develop this. And basically our focus was on what we would call physical geography, or the physical drivers of environmental change, and focused on a number of key aspects. For example, one of the aspects of the class deals with energy transfer between land and air. One of that forms is incoming solar radiation. That's radiation from the sun. And that's really absolutely critical, because that's what really drives many of the other processes that go on. We also focused on energy balance. This means that we're not only focusing on the shortwave part, which is the sun, but we're also focusing on the long wave components. And that's things like the heat emanating from the surface, as well as the counter radiation we observe coming from the atmosphere. And of course, we also focused on some really important physical properties of these surfaces, of which one of the most important is albedo. That's a measure of the amount of the incoming radiation that's reflected back and therefore not absorbed. Another key environmental driver that we focused on in this class is temperature. Temperature drives things like photosynthesis, respiration, evaporation rates. And we were interested in learning how that changed seasonally, across space, vertically and diurnally in the air, as well as how it changed in the below ground soils. Water, another key environmental control. And so they're, again, interested in the daily changes, seasonal, regional, and atmospheric moisture, but also focusing on what's going on below ground in terms of seasonal and vertical changes in soil moisture in response to rain and drying. Finally, really interested in some integrated measures. And one of the most important ones is this idea we call potential evapotranspiration. That's the amount of water that would evaporate or transpire from a surface if there was no water limitations. And that's an important variable because it brings together all these other parts of the environment, the sun, the energy balance, temperature, and water, to allow us to study this. And also, we can also look at this in soil water balance. And a lot of this was also linked to plants and how they responded to these things over time. So how was my plans for student who learns? Well, you know, there had to be some lecture, about half the class is lecture, and this is really designed around the fact that many of the students who actually took this class had no physical geography background. They never had much of this, and so I had to give them something to work with. But the real key learning comes below. One of these is these research projects. So the students over the quarter work in groups to do 4 research projects. Sorry about that. And they cover a range of topics over the quarter, starting with insulation, then energy balance, then temperature and water. And then as a key part of this, they present it to the class, right? And then finally, a last part, again, getting back to what Chris was saying about the importance of field work, I really felt it was important that students had an opportunity to see the environment where these observations were made and do something in that environment. In particular, to take some field observations and link it back to the actual observations from the tower data in our final project. And of course, my key objectives are, 1, to provide a better understanding of scientific process. One of the most painful things I hear from an undergraduate sometimes is, I can't do science, right? And you know, that's because there's this idea that science is memorization, it's all these other things, but really science is asking questions, right? And that's more than anything. And then it's figuring out ways to test those ideas. What data would you look at? How would you analyze it? All those things are science. A key important part of science is being able to present what you find, right? So presentation skills. In this case, this is all built around the idea of physical principles that control microclimate, but it could have been any subject. It just happened to be, this is the one I chose to use. Research skills in the field. Students really need research skills. These are super valuable. Also, you need skills to work with data. There's quite a few different environmental data science kinds of degrees occurring in. And of course, finally, to better appreciate what science really does. So the way we did this now is we proposed to NSF, who funded this, that we would build a network of towers that covered a wide range of environments. And the Santa Barbara area is absolutely perfect for this. We have a coastal environment here, Colwell Point. We climb up the San Ynez mountain ranges to get to the peak. We come on down to the San Ynez Valley, and then we move into the valley up to another place, and in the interior we call Liskay Creek and Airstrip. And at the beginnings and the ends of this transect, what we've got is 2 university reserves. So these are places that are really easy to work in and really designed to help us teach what we need to teach. In the middle, we even have a couple of other stations, but one is Painted Cape. So one of the key sites, and the one I'm going to talk mostly about today, is Colwell Point. This is what we would call an invasive grassland. It does have some native plants, such as blue-eyed grass and saltgrass, but it also has a lot of imports, like fennel, lots and lots of invasive Eurasian grass species, and things like, for example, a wild radish. It is our lowest elevation site at 6 meters. It's also the first site we built, and here we again use this as a learning opportunity. Chris Still and I co-taught a graduate, undergraduate level class to have students participate in the idea of, where would we put one of these kind of towers? And then finally, each student was assigned an instrument. They learned about the instrument and they deployed the instrument in the field, and they were responsible for initial testing of whether it collected what we thought it did. And that led to Colwell Point Instrument Tower. This is our most high-end tower. It has the most goodies. On the radiation side, we have a standard light sensor that measures sunlight, but we also have this thing called a 4-channel net radiometer, which I really love. It takes that shortwave component and measures it. It comes down from the sky and reflects off the surface. And it takes that long wave component as it's emanated down from the sky, and then it's emitted back from the surface in the form of heat. It had ways of measuring water, and this is a precipitation tipping bucket. Also, we did fog collecting and leaf wetness sensors. For wind, we have a marine grade anemometer. For a measure of the flux of vapor, we had 2 temperature relative humidity sensors. This allows us to do what's called a Bowen ratio, which is a gradient-based method that allows us to use the vertical gradients in water and temperature to get an idea how much water is moving away from the surface. We added a substrate a technique. We looked at soil, and we did 3 depths for soil and temperature probes. We added phenology with a webcam system, and then lately we are communicating with a wireless help of with the help of Tony Nelson, which means we can get the data anytime we want. Now, we also need access to the data. And this, again, is a case where we engage students. This is the Innovative Data Set for Environmental Analysis by Students, or IDEAS website. It was supported by an instructional improvement grant from UCSB. And the key thing is to give access to data, but also it adds some graphical tools and lots of tools for data exploration. If you want to learn more about the kinds of measurements we make, it has a really nice background section. And of course, it is the primary means by which we communicate. So this is just one example of what we call the WX view or weather view. This has many classical measures that you'd see in any sort of Met station, like temperature and humidity, wind direction, wind speed, leaf wetness is not standard. Solar is pretty standard, and of course, rain and fog. And what this allows students to do is explore the data, right? They might say, okay, I would like to see what it was like at this time. They can just go to a calendar and find the data for that time. They can display a range of time. They can say, I want to see a month's worth of data and see how it changed. They can do that. They can display over a year's worth of data. Then once they get what they want, they can download the data and you get what you see. So in this case, if a student wanted to download this data set, they would get all these things at once. They could instead focus on an individual measure and just download that. And this can be accessed through any standard internet browser. We have similar measurements for the soil and the radiometer. So here's soil temperature, and you see the temperature patterns. This is showing over a period of about a month. Actually, that's that's about a month. This is soil moisture, and you see it jump up here. That's following a rain event. And this is the long wave and short wave radiations. You see the daily patterns playing out. And of course, we have some other stuff in there. And so this idea also comes back to another thing that I've had as a long-term interest at UCSB, which is designing labs that are alive, that change with the changing environment. I've designed a lot of labs. Many of them are these sort of hardwired kind of labs that you do A, B, C, and D is the outcome. And it's the same for everybody every year. And I really don't like that. I wanted labs where the kinds of questions you might ask change every year because the environment is changing all the time, right? And so here's just one example. We've been collecting data since 2008, and this has captured the most severe drought in Southern California history for 1,200 years. So this means we've got these amazing research opportunities that students can do working with these data. And so we kind of think, what kind of questions might you ask? Now, on another part of the training side, we do a lot of field training. So basic training, our sampling unit is the classic vegetation transect. So we have a series of fixed transects out at Colo Point. If you ever see those little plastic caps, those are the beginnings and end. There's one in the middle. And for there, we lay out a 50-meter line. And for that, we played on what's called quadrats, which are these 1 meter square little plots. And then we say something about 2 really important properties. One is what's there, that's the species and composition and diversity. And 2, what are the properties of that surface? What's the green cover? What's live, what's dead? How tall is it? How hot is it? What's its albedo? And so here we're seeing a student laying out the line, and here's 2 students taking some of our photographic data. And so a real key thing here is species composition. And so we basically teach students the basics for figuring out what you would do to figure out what's present. And here's one of my students working with a quadrat. And here's 3 students. Now, often they work in teams because they come together to agree on what they think is present. You can't really see it very well, but because students don't really know the plants, this is a plant guide we built for Colo Point. And what it does is it has pictures that allows students to identify species. And that all ends up on a data sheet, right? And so we have these data sheets. So every transect and quadrat we've ever measured in the entire history of the class is stored on these data sheets. I like to know the names of the students who did the collection. Then the name is the location. Then there's other things like time and date. And then these are all these sort of species codes. And these are basically genus and species You don't have to know these so much, but things like amps is Amsynchia, Silostaca, etc. And then we have the students very quickly figure out is something present or absent, and that's just a 1. For certain focus species, we actually have them count them, and we counted 2 native and 2 invasive species. The frequency is quadrants. So a quadrat can be divided into smaller sections. And so students count those up, and that's kind of like a poor man's version of a way of counting abundance. Then we use a simplified cover scale called the Brown-Blockett scale that takes this big range and divides it into 6 simple numbers. And of course, we also do phenology. This all ends up being compiled in an Excel spreadsheets by students. It also ends up in Excel in an Access database, which is then accessible to every student who's ever taken the class. So this gets into another key concept I like, which is learning across generations, because scientists don't learn something in 1 year. We learn across generations of research projects, and scientists and students can do as well. So then just to show you what some of these data might look like, these are some of the focus species at Colo Point. This is just a normalized count of the number of plants along transects. These is dates we've been in the field. This is Plantago lanceolata. This is a plantain. This is fennel. And this is blue-eyed grass down here in the blue. And what you can see is there's a lot of change from 1 year to the next. For example, you can see there are years where the cibi, the blue-eyed grass, is really is very common. And so someone interested in flowers might want to know, well, what are the conditions that cause these big blooms? Well, at the same time, Plantago lanceolata, the plantain, was very low and then suddenly exploded in 2015. And for those of you who know what happened at Colo Point, that was following the tank fire, right? And part of our area burned, and that gave students about 3 years to figure out what a fire does and how post-fire recovery looks. Now, for the physical measurements, I use a lot of quantitative approaches. These are not just simple estimates. And so one of the techniques I've worked on and developed was a systematic way of collecting pictures of surfaces, basically a camera system, a cheap camera system pointing down over a fixed area. It has a little light bar for a standard, a little 3x5 card where we write down the name of the transect and the quadrat. And then within that, we take a picture, and then we also measure height, another biophysical measure at the top, left, center, and bottom, and right for both the dominant and codominant species. Recognizing that these students who are taking this class may never, ever have a remote sensing class, we designed a MATLAB tool that allows them to do some pretty high-end processing. So basically, this tool allows them to load up all these JPEGs. So you can see these are paired photographs. Here's one that has the card for information. Here's the one that does not. This means we never lose track of what we're looking at. Then you can crop it. So what they do is they crop it here, and then they classify an image, and they've done this all in batch, and then they output to a CSV file for later analysis. And this is what the classifying algorithm looks like. It's basically a binary decision tree that just basically does a bunch of splitting rules based on things like green light, red light, the ratio of green to red light. And what that takes is this photograph here, which you see some dead plants and green plants and some yellow stuff, and it turns it into a classified product, where in this case has 35% green cover, 19% shadows, 46% non-photosynthetic vegetation, flowers that are blue and yellow. And now that we've done this, we can start looking at these same sites over many years or different seasons and saying, what's going on? How's it changing? So for example, if we look at early April in 2011 versus early April in 2013, these are very different years. 2011 was pretty wet, 2013 dry. Yet if you look at them, they're not that different, right? And you might ask why. And of course, one of the reasons why is when the rain did fall in 2013, it came late, right? We can then compare 2015, which was roughly comparable, a little drier than 2013. And we see, and this is a case where it's much, much more senesced. This is the dead plant materials, the red stuff. And then finally, we look at April 2019, and we can see here it's much, much greener. And of course, that's actually not that different in terms of the total rainfall amount than 2011, yet very, very different response. Another thing, we're very interested in energy balance. And so there are two things we look at here. One of them is the albedo. Another one is this biophysical measure of height. Albedo is just the ratio of reflected light from a surface divided by the radiation coming from sun reaching the surface. And the way we did that is we took a apogee radiometer, a little light sensor, attached it to a spatula I bought at IKEA. I put level bubbles on above and below the spatula, and that allows you to then to take this sensor, measure stuff coming down from the sun, flip it over, and measure it coming off the surface. And then you can begin to see how albedo, as shown on the y-axis, changes over the different months. And we see, for example, it starts off a little dark, and then plants get more reflective when they hit peak growth, and then they begin to dry off again. Meanwhile, if we look at height, we see that the height pattern is very different. And actually, the plants are tallest later in that year, later at the end of April, as they continue to add more height and more biomass. We also have a few other field measures, and one of the ones I'm particularly interested in is temperature. There's been a revolution in the kinds of temperature measurements we can do of our surfaces. And what we're finding is that the actual temperatures of surfaces are very different than the theories say they ought to be. And we're learning a great deal about that. And so this was something that Chris Still and I wrote a proposal again, was funded to get some thermal sensors. This is a FLIR, an imaging camera. And so this is Brittany Gale measuring a thermal image. And then that allows us, again, take this image, classify it in different kinds of cover like green veg, shade, and NPV, using, again, tools students can use, and then looking at the temperature patterns as they vary by the cover. If the solar conditions are cooperative, we sometimes bring out some really high-end instrumentation. A spectrometer, this is a spectrometer on loan from the Jet Propulsion Laboratory. And in 2019, we had a great day. And so we brought out this spectrometer, and the students could, in addition to all these other measurements, measure the very fine changes in color of all these surfaces as a function of very fine changes in wavelength, all the way from the ultraviolet out to what they call the shortwave infrared. So now I'm going to switch over to talk about some student projects. There's been many of them, so this was a very painful process coming up with just 2 when I have over 60 to choose from. But here what I'm talking about, the effects of sea salt and salt aerosols, and this was done by students Cristina Gonzalez, Kai Funakawa, Kyle Ege, and Will Underhill. And they had this simple question: what is the effect of sea salt aerosols on optical thickness at Colwell Point? So to give you an idea what optical thickness is, it's a measure of how dirty the atmosphere is. So if the atmosphere is really clean and there's nothing in it, the optical thickness is low, right? If the atmosphere is full of junk and it's very opaque to radiation, the optical thickness is high. And what they hypothesized is when the wind is coming from the southwest and blowing over the ocean and carrying all these sea salt aerosols, that's going to make the atmosphere look dirtier, and it's going to raise the optical thickness. Right? One of the things I really liked about this project is the fact they used history, right? They went in, and what they did, and rather than just sort of arbitrarily picking a wind speed to work with, they went all the way back to 1805 to look up the Beaufort wind scale. And they looked at these various categories and said, hey, look at this one: small waves, numerous whitecaps, lots of production of aerosols. So let's pick 15 miles per hour, right? Then in addition, they want to look at the dominant wind speeds, one directions, one being directly off the ocean at 270, and the other one being coming in from the north, from the interior. Another set of the kinds of tools we give is some basic graphic tools. So what this is showing you, and this is some MATLAB code we wrote, this is a wind polarogram or a windrose. And this is the size of the little wedge, tells you how many observations came from that direction. So you can see here, most of the wind is either coming from the west to southwest, or it's coming from the northeast. This is a similar kind of plot, but now what you're plotting is an actual data point. So the location along this radius is the azimuth, the direction it's coming from, and the distance to the point from the center is the wind speed. And what you can see here is, although a lot of wind is coming from the northeast, it's not very fast, but the wind coming from the west is really fast. So then what they did is they took the light sensor and they did some really interesting math you can do that involves all kinds of models of the sun and its light angles to calculate optical thickness. And what they found is if you look at the northwest, 270 to 360, In fact, the higher wind, the ones coming off the ocean, had statistically significantly higher optical thickness. So this is consistent with their hypothesis. If you look at the wind from the southwest, also from the ocean, it's not quite as extreme, but it's still there. You look at the northeast, these are these lighter winds that come in. You don't see it, right? There's just, it actually turns out the air is cleaner when it's the higher wind speeds. And I suspect that has to do with storm systems. And then finally, if you look at the southeast, it just turns out the southeast winds never produced high winds. The second one is a temperature one. This is the third environmental variable we're looking at. And this was by Henry, Jose, and Chris. And their hypothesis was that wind direction and speed can be predicted by temperature differences between two near locations, that the higher the difference will lead to more intense winds, and the wind will change its direction depending on the gradient. Where is this coming from? This is coming from your classic air-sea breeze. So if you look at this, this is the Santa Barbara area. So here we are in the interior, up here towards Ayers. Down below, you see Colo Point, and you see the ocean. And what we know about the ocean is it's a really big heat sink. Energy goes into the ocean, the temperature doesn't change that much. Energy leaves the ocean very slowly. The temperature doesn't change much at any time, day or night. Land, on the other hand, has very little water, shows much more dramatic temperature fluctuations. Then the next thing to remember is the temperature gradient has effect on pressures. So if you have, for example, high temperatures, that means air is rising. That's a low pressure system. If air is the surface is relatively cool, that means air is sinking. So what we've got is high pressure and low. So you would expect to see winds going this way during the day when the temperature here is hot. And then at night, we would expect them to reverse directions. So then what they did is they took all these data sets from different times of different seasons, times of the year, and they did a temperature difference. They said, okay, let's take the air temperature at airstrip and subtract from that Colo Point, right? So what that says is that when the air temperature is higher, that would be a low pressure at airstrip. That would be a case of a positive number, and that means that's low pressure at the airstrip. That means that the air should be flowing one direction towards the interior from the west. And when they connect the dots, that's exactly what they find. You see these bars that are all sitting there at 300 degrees. If we get the negative pattern where Colo Point is warmer than what we see at the airstrip, you would expect to see the winds reverse directions, and that's these blue arrows. And you see that holds true as well. So they were really pleased to see that it actually works. They also looked at the absolute value of the difference to see if that had anything to do with wind speed. They, in fact, did find that the bigger the temperature difference, the higher the winds. But they also had to keep in mind that winds can be pretty strong during winter storms as well. And that kind of messed up a little their analysis. So I'm going to conclude with just a statement that this has been focusing mostly on the educational side. I also do a lot of work in with remote sensing. That's most of my training and the reason they hired me at UCSB. And I've also worked with a fair number of fairly advanced data sets. One is called AVRIS, is an imaging spectrometer. It collects spectra from an air. And MASTER is is a sensor that includes visible and thermal bands. And through a variety of programs, such as the NASA Student Airborne Research Program, and the fact that I've written lots of NASA proposals and involved in a lot of campaigns, there is an immense amount of data over this entire region. In fact, if you look at the maps, we probably sampled the Santa Barbara region more densely than any other place in California, except maybe calibration targets. Another really interesting data set that's also was just recently acquired in 2022 is the NASA SHIFT campaign. I'm not going to talk about that here at all, other than to say that Dana Chadwick will be coming to talk to you about SHIFT on October 18th. But I will say that while Dana and the others were mostly focusing on these flights between the Sedgwick Ranch and the Dangerman Preserve, many of my students were running around in the wetlands of Colo Point doing our complementary measurements. And so with that, I'm really happy to answer questions, and I hope you enjoyed what we saw. These are my SARP students from, I think it was 2016, and there's a thermal image of them.
Wonderful. Great. Thank you, Dar. That was so very interesting. I have a lot of questions for you too. First, I'm going to just remind the audience out there how to use the Q&A function. You're probably all super pros at Zoom by this point, but at the bottom of your screen, there's a little button and you can click Q&A, and you should drop your questions for Dar or Chris in there as well. So I wanted to say a few things. One, I'm not sure if you all know this, but Professor Roberts is globally known for the high tech and really advanced research that he does. And there's something very comforting about knowing that Nikea spatula is also one of his instruments out there in the field too. So I guess it takes all kinds of things to make science work, and that's really exciting. I'll actually start with the first question for you, Dar. And, I think it's really neat that you can get your students out there just, hands-on and like not only in the field, but also working with the data and working with the equipment. And could you tell us a little bit about maybe where some of your students have ended up? When you come and take a class in the geography department from you, where does that lead you to?
Well, it depends on which class they're taking, but in this particular class, this has been sort of really well tuned to getting students ready for a lot of these environmental management and data and analysis majors that are coming on. This is a lot of masters and PhD programs going in that way. So for example, one of the students I was working with just this last year, he ended up at University of Michigan in one of these environmental data science analysis data science master's programs, and he used for his first project in the first class he took was one of the projects he had for my class. And working with the professor was so excited about that, he ended up accepting him on for a PhD. And so now he's doing a PhD. He's not doing this anymore with the PhD, but it was that got him in. And then I have another student who's at Woods Hole, who is doing very similar things to this using environmental analysis. She's mostly working with models, but she's doing it for the entire planet Earth, right? So it's a really exciting kind of thing for her. And other students I've worked with have used this to go on to get to get into PhD programs and do really interesting work on diversity measurements at places like UC Santa Cruz and UC Davis.
Exciting. All right. Well, here's a question from Catherine Keach. And Catherine asks, with the many years of temperature data you've accumulated, if you look at the annual averages of that data, do you detect a warming trend?
Well, that's an interesting question. Normally, one would say that it's kind of risky when working with a data set that's really only like 15 years old. And there is a lot of interannual variability. You do see hints, though. I often warn students when they pick that as a project for things that's a risky one, because no climate scientist is going to feel comfortable with only like a 15-year record. But actually, one of the things that Eamon Espy did find when he looked at the cloud radiation budget and things, that those had shown significant changes over time. And in fact, Park Williams, who will be giving a talk in about 2 weeks, used these data sets as part of some other data sets to demonstrate that there have been changes in the length of the fire season because through changes in cloud cover, and that you can actually see these sort of changes over time. And Park has actually shown at nighttime temperatures have actually been going up over time.
So you also, I'll just kind of tag on to Catherine's question. You mentioned that the Santa Barbara area in particular is one of the most imaged using Avaris or other technologies too. So what and I think this kind of observation goes back a long time, longer than 15 years or so. And so what is it that the imagery data can help teach you in addition to the temperature data? How does the imagery data really give you any more insights?
Well, we've done a lot of work in all kinds of different areas. And when we're looking at natural vegetation, we've been mostly focusing on the effects of droughts. We've done a lot of work more recently on what happens after fires. So for example, we've done a lot of work following the Hazazita fire, the Whittier fire, the Sherpa fire, the Thomas fire. Also, it's been change in the landscape mostly in those kind of things. When we go to the urban areas, we've done a lot of work on urban heat island effects and urban water use in trees. And if you even go off the coast, and this is sort of like, they saw a request for me collecting cans of air out at Colo Point. We actually do a lot of work with methane. And so you might not realize is that Colo Point, there's a world-class methane seep right off the coast that literally bubbles methane up like a jacuzzi. And much of the techniques we're using today to monitor methane from space and from air actually were developed off of Colo Point using AVERS data.
Yeah, wow, very, very interesting. That's great. So another question that I'll essentially add on to that, like how do you inspire your students who say things like, I can't do science, you know, and you know, we heard it from you a little bit tonight. You know, I really enjoyed hearing that you know, science is just asking questions and moving through that. So what are their tools as an instructor, as a professor, as an advisor that you kind of, what advice do you give to young students today about getting into the sciences?
Well, I think that you know, it's harder to do at the really lower division classes where we're often trapped with the tools we've gotten to things like scantrons and bubbles and stuff. You know, we can inspire students with the way we speak and the problems we deal with, but you know, it's harder for them to get around this idea there's a lot of memorization, right? Right. But when you get to the upper division level where you can do projects, I think that's really where you can really take off. And so, for example, one of my students I really liked working with in this class, Measuring Our Environment, the first week she came in the class, she came to me and said, I'm really frightened of this. I'm afraid I'm not going to be able to handle it. I don't do science well. I'm not quantitative. And I said, you know, come on, you know, let's stick it out. I'm giving you the tools. You're going to do fine. It's all about the questions, right? And anybody can ask a question, right? And you're working with a team, and team members can bring in your shore up your weaknesses. Just go for it. She just blew away the class. She was so good in the class, and now she's doing a PhD because I just wrote her a letter of recommendation. And she was part of this sort of dream team group that was just every project they did, you're just kind of going, whoa, this is amazing, right? And to me, that was just an amazing thing to see. And so I think making people realize you can do it, right? And then one of the best ways to demonstrate that is to give someone an opportunity to actually do it, right? Some of the other students were a little afraid. They just loved the field work, right? They got on the field and they said, well, this is what I want to do, right? And there's plenty of places where people being able to collect high quality field data is a valuable tool, a valuable skill.
Oh, thank you. So, well, Chris, you want to ask this question?
Sure. The question is from a lot of students that I know are thinking that right now. How can I get a job in geography? What can I do? What kinds of jobs are out there?
Oh, well, I feel kind of guilty answering that one. It's a great discipline for getting a job. Basically, at the undergraduate level, a lot of our students take the remote sensing and geographic information science courses, and they just get snapped up because everybody needs somebody who can deal with spatial data, whether you're city planning or whether you're an ecological group of the nonprofit working in some area. You're just bombarded with spatial data, and those are the tools we teach. At the graduate level, our students get snapped up before they finish. I mean, I often tell them, no, don't take that job until you're done, because it gets harder to finish a PhD when you're working, right? And so it's a great discipline to be in. I think mainly, and it's just going to get better. Right now, we're living in a renaissance of remote sensing. Not only is the United States launching a lot of things, they just launched an imaging spectrometer called EMIT. Their Germans launched one called NMAP just earlier. The Italians launched one called Prisma 2 years ago. There's a whole suite of sensors being launched by the Europeans. We have on plans another launch that's going to occur around 2028, which is going to be called SVG. And there's an incredible hunger for people who actually have the skill set for working with these data, and there just are not enough of them, right? There's people just struggling to find postdocs to do anything because there's so much data to work with and so little talent to work with it, that it's a great place to be.
Yeah. Yeah, hear that, everybody out there? Take Dar's class, and then you'll get a job in data science after that. All right, so the next question comes from Mark Holmgren. There's actually two, but I'll ask one at a time. The first is, how does the 2013 to 2016 drought compared to the current drought? Is this one extended?
I would say in some ways the 2013 to 2016 was a little worse, but it's not because of any absolute amount of rainfall. It's just because the 2013 through 2016 was just every year was bad, right? So we had 4 years where it was really bad. And if you look at the soil moisture, you can actually observe that at some point in time in the drought, the water never even reached the deep levels. So one of the things I've been pointing out to a lot of people is that if you imagine trees are relying on deep soil water, they've got these deep roots. Well, initially when the drought hit, the trees just rode right on through it. They were not really affected. But then once the water was used up, it's not getting back down there because we just haven't had storms. Now, lately, I would say this year has been exceptionally bad. We had a lot of rain in December, but nothing from January on. So if you look at the hydrologic year for this year, it's not going to look terrible. But if you look at the calendar year, it looks really bad, right? And it is really, I think, in because we haven't forgotten the drought from 2012 to 2016. That's still carrying over on a lot of the plants, especially the deeply rooted ones. This last one, I think, is really having a bad impact. And I think if Lee Andrade talks and his group and Anna Trugman, they can point out what's happening to things like the blue oaks, which are really, really in a bad way.
Yeah. Yeah, absolutely. And Lee, of course, is a faculty member in the EEMB department here at UCSB, and also doing research out at Sedgwick Preserve too. Okay, so here's another question from Mark. As a scientist that actually looks at close-up data, how would you steer public perception of climate change as opposed to what we hear from the press? The press tends to highlight and sensationalize individual events. Where does the balance lay? So there's a big question for you, Dar.
Oh man, I don't know if I even know how to answer that, right? Because it's like when I talk about climate change, I tend to revert back to some just basic physics, right? That the basic physics basically says that even if you take a relatively weak absorber like carbon dioxide, but you're still absorbing more radiation, and that causes the atmosphere to heat up a little bit, then that causes another thing to bring into the atmosphere, which is water vapor, which is even a stronger one. And just the basic physics says there's going to be a lot more absorbing in the atmosphere. And if you really want to think about it, imagine the case of what happens to you if you put a nice big thick blanket on and you find yourself trapping all that heat. You get warm. And that's what's happening to the Earth, is we're getting warm as we're trapping more and more of this heat into this system. And but it is hard to avoid the sensationalism. And I think sometimes the sensationalism is important, right? It's pointing out that hurricanes are getting stronger, that they're causing more damage. These are all important things. I think the public seems to resonate more with that than the telling them the basic physics. Yeah. So I wouldn't say I'm necessarily the best communicator when it comes to climate change itself, other than the fact that it's clearly happening. We see it at night. Nighttime temperatures are going up, and it's actually clearly important because it's beginning to kill a lot of people and plants.
Chris, go ahead. So Dar, your data seems to be really great too, to look at really broad spatial scales. How useful it is to look at really small scales. And the reason I'm asking is we do restoration and we see a lot of microenvironments. I would love to know more about the physical environment when we decide what to plant where.
That-
Can that kind of data be used at that small scale?
It can, it's a little tougher. The kinds of where you really want to start looking at when you're looking at super fine scales is on the remote sensing side. We're talking about UAVs, right? So now you're talking about aircraft systems that are where the spatial resolution's down to a centimeter. And then you can start actually seeing that really fine scale patchiness of the landscape, because we all see it. You see this little, like if you go to Cole Point where I work, there's little parts where you have Brachypodium distichum in one section, you have Lolium plane multiflorum in another. It's like, and it's like they're not far apart, right? It's a very, very fine scale variability. You can also do this with LiDAR systems that are now, you can get very, very high, what they call point densities. For the environmental observations, there are sensor networks that are going in. So for example, you can imagine if you were interested in studying these fine spatial patterns in a grassland, you could literally put a network of soil moisture probes in and begin to look at those things and see how they vary as well. But those are a little harder to do because, you know, that's more like basic ecology. But when someone's asking, can you see the big changes occurring in Santa Barbara? If all you've studied is one grassland, they're a little disappointed.
Or maybe satisfied in a different way. Excellent. Well, all right. Well, thank you so much to you, Professor Dar Roberts, and also to you, Chris, our director of the Coal Oil Point Reserve, and also to everybody out there in the audience for tuning in. I wanted to just let you know about next week's seminar, which you will be bummed if you miss out on. We will have Gina Bental of the Sea Otter Savvy at San Jose State University presenting the sea otters of San Luis Obispo County, what they teach us about Southern sea otter natural history and conservation. And that is out of our Kenneth S. Norris Rancho Marino Reserve located up in Cambria in San Luis Obispo County. So please don't miss out. Also, tonight's seminar will be posted on the UC Santa Barbara Natural Reserve System YouTube site, where all of our seminars from this year and the last 2 years are also posted. So please do check them out. And again, thank you everybody for joining us. And I hope you have a wonderful evening and hope to see you next Tuesday. All right. Thank you.